from bulk crystals to modeling of surfaces. I decided to illustrate this idea on perovskite, which is cubic. Remind that calcium titanate is cubic crystal with simple cubic lattice. And in cube, there are different directions. Direction along one of four sort of axes is 0, 0, 1. Direction in the diagonal, in the face of cube, 1, 1, 0. And direction along the third order rotation axis is 1, 1, 1. So what people do when they try to model surface, they use so-called slab model. Let's see what happens if you consider different symmetry slabs for perovskite. Paldies. Un tagad man būs vieglāks tas. Paldies par. Nobody knows before calculations which cutting gives you more stable. Formally, of course, for perovskite it's well known, but for more complicated systems, you need to calculate different slabs and compare formation energy, and to see which one is more favorable from energetic point of view. Of course, you understand that for simple structures this is well known, but for more complicated, it requires some additional work. Let's see what happens when you take 0, 0, 1 cutting. What it means 0, 0, 1? It means that you take this cube, which consists of strontium, titanium, calcium, titanium, oxygen 3. When you model surface, you have AbO3. A is calcium, B is titanium, oxygen is O. So you have two planes, AO and BO2. And then you take this slab, AOBO2, AOBO2, and so on and so on. In this case, you have two periodic lattice, because along this direction you have no more atoms. You decided to cut out slab to model the surface. And now question, which, you see what happens. If you have the integer number corresponding to the bulk, you will have up AO and down BO2. So you will have dipole moment along this direction. Now it's your choice. You have other possibility. For example, to take odd number of AO or odd number of BO2. Then in one case you will have AO here and AO here. No dipole moment. Traditionally, it's used such picture because then you will have, you are interested in surface energy. You are interested in what happens with bulk system when you cut out some slab. Slab is huge. Your possibilities on computers are not very powerful. So you need to investigate the convergence of the results when you increase the thickness of this slab. And what is criteria? You take central plane, but central plane you can find only for odd number of planes, and see when, for example, charge distribution on central planes is stabilized. So it means that adding on next outer planes will not change anything. Therefore, first model is this one, without dipole moment. You see here we have 1 AO, 2, 3, 5, and BO2, 1, 2, 3. But we can consider also vice versa, when BO2 is the highest and lowest. And energies are not the same. And now on this peer chemists who decide, for example, if they consider some adsorption, then they analyze which surface is, for example, of water adsorption more favorable. What think chemists, I mean young chemists, Sasha, Andrei, what do you think? For if you have water molecule and your grant requires to analyze adsorption of water molecule on the surface. Experimentalists formally do not know with which surface they work, AO or BO2. They can say sometimes can, but sometimes not. What is AO? AO is calcium oxygen. What is BO2? Titanium oxygen 2. What do you suggest?
No, to calculate energy for both
calculate,
surfaces.
but before calculation. It depends on the chemical bonding. Now I go away from crystallography. You see that in perovskites, calcium and strontium and other, they are practically ionic. Calcium 2 plus, strontium 2 plus, and in calculations, Dima, when you made calculations, you calculated charge on this A atom close to 2, something like plus 1.8 or something like this. But bonding between titanium and oxygen is essentially covalent due to the electrons of titanium. Therefore, this bonding is stronger. So, when you consider AO surface, you have ions of A and oxygens, formally 2 minus, but not 2 minus because they are on the surface. So it depends on the position of certain molecules. This is as a story. I have no time to go into details. I simply, as I'm speaking about symmetry, I simply say that these are two periodic groups. And distribution of atoms over the planes depends on this direction. You see that in this case, you have 1, 1, 0. This is diagonal plane and different distribution. And in this case, this ABO is absolutely unreasonable from chemical point of view. What is this? Calcium, titanium, oxygen. You see that all valences, formal charges are not reasonable from. Therefore, it's reasonable to consider the slab finishing by oxygen. And in this case, you have third possibility. What is necessary to understand? That when you are interested in the surface properties, you need to analyze which cutting of the surface from the bulk crystal is the most favorable. And this cutting depends, of course, on the symmetry of bulk crystal. This is rutile. And for rutile, you have, this is unit cell. Again, this is simple tetragonal lattice. 1, 0, 0, 1 is along that axis, and so on. 1, 1, 0 is diagonal, and 1, 1, 1. And you see that why in cubic crystal I haven't written 1, 0, 0. And here I write separately 1, 0, 0 and 0, 0, 1. Why? Who can say? Don't forget that that was cubic, and therefore also directions 0, 0, 1, 0, 1, 0 and 1, 0, 0 were equivalent. But this is tetragonal with C translation vector, which is larger. Usually larger or smaller, it doesn't matter, which is different from two others. And therefore 1, 0, 1, 0, 0 and 0, 1, 0 are equivalent. But 0, 0, 1 is not equivalent. Is it clear? Or not clear? Okay, and now maybe this is the result. I have no time for detailed analysis, but I simply wanted to show you on the rutile of example, what happens if you consider different surfaces with different index, 001, 100, 101, 110. Then you have two periodic space groups, which depends on the number of planes, even or odd. I already told you that you can take both in the perovskite and here also, even or odd number of planes. Let's see, 110, you have titanium 2, oxygen 2, and oxygen plane. And you can regulate in such a way that oxygen, then titanium, oxygen, titanium to oxygen 2, and again oxygen, and so on. But in this case, you have absolute class structure, oxygen 2 and titanium 2. And in this case, it's very interesting. You have planes consisting of only one type of atoms. And when you consider the surface, you can take the upper surface of oxygens or titaniums. In this case, you have titanium oxygen 2, titanium oxygen 2, as in bulk, but on planes. So you see that the index of surface defines the distribution of cutted planes of atoms. And it is different. And when you consider slab model of surface, you need to take into account. As for symmetry, it is also different. And now I'll show you and return to this table. I would like to say, and it's interesting, that any layered space group is subgroup of some bulk. It is unpleasant table, but it's very simple. I explain. What is layer or diperiodic group? As I already told you. This is group where you have three-dimensional object, this slab, but only two translations in two directions. Third translation is absent. And therefore, about, I think it was at the end of 60s, when all the diperiodic groups, or layer groups, G is space group from those 230, which we already discussed today. And each layer group, or diperiodic group, is subgroup of some three-dimensional, or space group. But what disappears in the diperiodic group? Disappears all the symmetry operations, including translations, along the direction orthogonal to the plane. There are 80 diperiodic groups, and each of these groups is a subgroup of space group. For some general discussion, maybe it's not so important. But when you make calculations, it's important because the more symmetry you use in your calculations, the faster these calculations. Therefore, you need to know the layer group when you calculate, make calculations of surface group. So you see that for four different indices of surfaces, A, B, C, D, 4, you have space group, which is connected with layer group, different for even and odd number of planes. And international symbol of these are space groups here. These are space groups, written in numbers and written in I hope now understandable symbols of space groups. And this is corresponding layer group. And when you know this connection between layer group and space group, you can use symmetry in calculations of these surfaces. Why it's important? Because when you investigate the convergence of the result, of course, you have more and more atoms in this slab, and therefore the higher is the symmetry, the faster is your calculation. Therefore, it's very necessary to understand this connection between layer and bulk groups. Let's see what crystallographers say about diperiodic groups. They are called subperiodic groups, in the sense that this is subperiodicity. In three-dimensional case, this is normal periodicity, but you know what happens here. I need the same. So let's see. Wyckoff positions of subperiodic groups. Here you see 80 subperiodic groups, and you need to analyze the symmetry of your slab and then choose, and in table for rotile structure I gave it, then choose the layer group from this table. And for example, let's show layer group which has yes, Wyckoff. What I would like to show you that Wyckoff positions appear with three coordinates. Subperiod, choose it. Yeah, choose it. And now open. I would like to show you what happens when with Wyckoff positions when you have three period, two period. Now, these objects are three-dimensional. Therefore, x, y, z are here. But you have now, along the third direction, parts of translation, partial translations. I'll show you, we'll return to space groups, we'll find space group with the same symbol, but three-periodic. And you will see that there are different third coordinates, because there is three-dimensional periodicity, including this third direction for periodicity. But here there is no periodicity. Of course, as object is three-dimensional, maybe I'll do the following. I'll change to space group, and this remains layer group. And then you can see the difference in Wyckoff positions. You see? The same, but space group. And now let's see. 0, 0, 0, 0, 0, 0. These halves disappear because the translation along the third direction is absent. And these Wyckoff positions disappear. But Wyckoff positions with arbitrary z remain. Is it clear? We have no third direction for translation. So this is layer group, and this is space group. And this is very useful, because using this connection between layer and space group, you can analyze the symmetry of electron states and phonon states for layers, not only for bulk crystals, but for layers also. Because you know these Wyckoff positions which are occupied in layer, and compare with those which are occupied in bulk. So this is a very interesting field of research of surfaces, slabs, to periodic systems. I can close it, yes? Is it clear? It's very nice that I get to show you simultaneously, because now you can compare what happens when the third direction disappears. Third translation disappears. Okay. You help me please with this screen, and then work with this screen. Oh, I need to return to my presentation. If the idea of this slab layer groups is clear, I hope, then you understand that for any bulk structure, you can do the same. You can consider different indices of surfaces, but for syncoxide, which is layered, you see how simple look like these surface constructions when it is 0, 0, 1 along the direction connecting layers. And this table allows you to connect both types of group. This picture comes from the nanotubes. It's difficult to explain it, but I'll try to do it. You know, what is graphene? Graphene is one plane from graphite. And carbon nanotubes were synthesized in 1991 by Ijima in Japan. But graphene itself was synthesized in 2004, later than nanotubes, by Novoselov and Chaim, Russians who departed from Russia, and they received a Nobel Prize for graphene synthesis. I never could understand why tubes appeared earlier than graphene, which in our modeling of tubes is used for rolling up. I'll explain to you in some general sense what models are used for nanotubes. What is chirality, what is translation vector, and so on. I have chosen the simplest case, when you have graphene plane consisting of only carbon atoms in hexagonal two-dimensional lattice. This is graphene. Before rolling up, we need to choose two translation vectors. This is primitive unit cell of graphene. I show it. It is two translation vectors, A1 and A2. Angle between them is 60 degrees. And there are two carbon atoms in the unit cell. The choice of origin for two-dimensional lattice is chosen in the center of hexagon, not in the other. This is primitive. This is primitive unit cell. Now, to construct nanotube, carbon nanotube, we can choose two orthogonal translation vectors. And these chirality indices show you which translation vectors are chosen. What is important? That these translation vectors are orthogonal, because when you roll up one of them, this is R, then the second one will be tube axis, and therefore they have to be orthogonal. This is requirement necessary to form from them tube. What these indices mean? These indices mean first along A1 and second along A2. Let's try to do it. 1, 2, 3, 4, I'm here, and now 2, 1, 2. Is it clear that this is translation vector which was received translating along A1 4 times, I'm here, and then 2 times along this. So this is one translation vector. And second translation vector cannot be arbitrary. this needs to be orthogonal. And orthogonality relations gives this L vector minus 4 and 5. What it means? Minus 4, I cannot show you in the picture. This is along A1 4 times in minus direction, and then 5 times along A2. Believe me that you will be here. So first step is choice of chirality indices for future tube. R vector is rolled up, and L vector becomes tube axis. And symmetry of nanotubes after this rolling is defined by so-called line groups. And there is direction between line groups and diperiodic groups, which we discussed. Why you need to know this direction, this connection? Because when modeling nanotube, you always use some layer group, some two periodical system. In this case, I took simplest graphene plane, but there are no nanotubes, for example, from tungsten sulfur disulfide. And in this case, this is not atomic plane, but slab of 3 planes. Tungsten disulfide, if you remember, this is tungsten and 2 sulfur surfaces. So, in Physical Review B, it was published by one of mathematicians, this is mathematician, not crystallographer, the correspondence between line groups, which describe the nanotube symmetry, and layer groups, from which these nanotubes are rolled up. What is interesting, that in nanotubes, this rotation axis along the tube axis, it is screw axis, and the order of this screw axis is equal to number of lattice points of two-dimensional lattice used for this unit cell. If you calculate number of lattice point, do not confuse it with atomic position. Lattice point is center of this hexagons. And when you calculate the number of lattice points inside this unit cell, you will receive the order of axis of this nanotube. And this will be screw axis. And this screw axis appears because when you roll up this R vector, then these former nodes of plane lattice become paths of moving along the screw axis. I cannot explain better, but the idea is the following, that the order of axis in nanotubes can be arbitrary. In crystals, only 1, 2, 3, 4, and 6. In nanotubes, formally any. And I would like to say that, Yuri, help me please with numbers. In Moscow, there is an Institute of Inorganic Chemistry, and there works Professor Dichkov, who cooperates with Yuri Zhukovsky. And they published incredible paper in Physical Review B, where they considered more than 140 atoms.
Yes, 1,000.
100.
1,000.
Incredible. How it can be to calculate 1,000 atoms due to high symmetry? Because they considered carbon nanotubes with high order of this rotation axis, and use symmetry. They produced some program, that was their own program, which took into account this high order rotation axis, and they considered incredible number of atoms due to high symmetry. So symmetry is not only theoretically important, but it is practically important. The higher is symmetry, the faster works your calculation. Therefore, the best would be to make calculations of cubic crystal. what I know from our chemists. Organic crystals are very low symmetry systems. And therefore, they say, oh, can you calculate some crystal which consists of carbons and hydrogens? I ask how many atoms? Oh, about 500. I don't know. I have no computer for such calculations because very low symmetry. So I'm not ready to go into details of nanotube symmetry. This is as a story, and in my book on inorganic nanostructures, nanostructures calculations, I describe it in more detail. But I want to say that crystallographers knew also one periodic groups, but they called these groups rod groups, and they never knew anything about line groups. And those who work with line groups didn't knew anything from rod groups. In fact, this is particular case. Rod groups, one periodic groups, we will see now on the side, are groups with rotation axis 1, 2, 3, 4, and 6. And one periodic. Crystallographers know them, evaluated them, and never guessed that there exist line groups. Because in line groups, you of course have the same axis, but more and more and more. Let's see what crystallographers give about line groups and about Wyckoff positions. Now you know well what is Wyckoff positions. You have seen what happens with Wyckoff positions in two periodic systems. Disappears this parts of translation along the orthogonal direction. And now let's see rod groups with only one translation. Open subperiodic groups. You will please help me. Subperiodic, and now Wyckoff positions, and now rod group. Choose it. And especially, I again open the same, but rod group, the same point symmetry, 6-1 axis, plane orthogonal to it, and two sets of planes the same. We have 3 dimensions, 3 periodic, 2 periodic, and now let's see 1 periodic. Dimo, please open the same group for bulk. This is rod group. Only one translation, only translation along one axis. And Dima will open 3 periodic, and you see what is the difference in Wyckoff positions. Six, down, go down. MM, this one is. You see the difference? The difference is 0, 0, 0 is always the same. But you have here for 70 rod group only half of translation vector along one direction. Here it is Z direction. Direction of one periodicity for nanotube. And there you have also other directions and more Wyckoff positions. So you see that space groups, layer groups of 2 periodic, d-periodic groups, subgroups, when disappears one translation along z-axis, and rod groups where 2 translations disappear. And now I would like to criticize those people who work with plane waves. But this is not from group theory, this is from quantum chemistry. In nowadays quantum chemical calculations, there are 2 communities. One community uses plane waves as basis. Plane waves came from physics, from periodicity. Next lecture, I'll try to speak about Bloch function, about K vector, and plane waves came from periodicity of crystalline potential. And plane waves calculations always require three-dimensional periodicity. This is drawback of plane wave basis. When they make calculations for three periodic bulk crystals, they have no problems, because they have three directions of periodicity. But when they make calculations of surfaces, slabs, what they need to do, they need to add artificially add to third periodicity, and they repeat along the third direction the slab. And they have interaction between the slab. This is not pure slab. What they need to do? They need to take such a huge vector between this slab along third direction that they do not interact because it's artificially. And what they cannot do in principle, if they consider, for example, adsorption of charged molecule, charged ion on the surface, then they need to repeat charge system along periodical direction. And then this infinite Coulomb. They cannot do this. So they like, oh, we have taken 10 angstroms for this period and it's enough. Maybe for some system it's enough, but for some other system it's not enough. Is it clear, the idea that plane waves basis always requires three-dimensional periodicity? Therefore, when you consider systems with subperiodic groups, with periodicity 2 or 1, then you need introduce artificial periodicity to have 3-1. And then you have problem with these images of slab. And what about tubes? In this case, you have one periodic system, and you need to add 2 translations, and then you have 2 parameters. What is interesting also, I criticize plane waves maybe. Does here somebody who makes plane wave calculations? Andrei, when I criticize, then you try to answer me that I have not tried. You use BASP. BASP or not?
Yes.
BASP, okay. Then he will try to criticize my critics of plane waves. So you see, this is the first problem, and very important. And second, that they cannot calculate, for example, adsorption of radicals, which are charged usually, ions or charged radicals. But every drawback has some good properties. They have no problem of basis choice. They increase number of plane waves, and of course it may take a longer time for calculation, but it doesn't matter for them if they have good computers. We use LCAO. Dima, you use LCAO or you
No,
also?
I'm also from plane waves.
Ah, so you have
Plane
experience in
music.
both. Okay. We prefer plane waves. LCAO. I work at the Department of Quantum Chemistry, but this is at the Chemistry Institute of St. Petersburg University. And chemists never have no idea about plane waves. They are interested in what happens in molecule when atoms form the molecule, how the atoms are distorted in the molecule. Therefore, they move from atoms, and therefore atomic basis is used. And when you use atomic basis, it doesn't matter the periodicity. You simply exclude those directions of periodicity which are absent in slab or in nanotube and make calculations. This is advantage. Disadvantage, where you need to take this basis. For molecules, it's simple. There are databases of different accuracy atomic basis, and chemists use them without any thinking where to take them. But in crystallized solids, the situation is more difficult, and the use of free atoms wave functions is dangerous, because in crystals, the tails of these wave functions are distorted, and you need to change the tails of wave functions taken from free atoms. This is disadvantage. Now, Andrei, what can you say about plane waves? Do I criticize fairly or not?
Yes, you do.
But why you use plane waves? You calculate only three-dimensional crystals. You are lucky that you didn't. Okay. Soon I'll finish, and what else in my presentation? This is for next time, but I'll begin. Now, all is okay, but you know that electron and phonon states in crystalline solids, you know this from band pictures, from phonon dispersion curves, which you'll find in literature, that they are classified by symmetry of the corresponding groups. For example, for bulk crystals, by wave vector k and some point symmetry connected with these wave vectors. At this moment appear something new, appear irreducible representations, both of point groups and of space groups. What is the difference between molecules and crystalline solids? In molecules, you have point groups, and then it's very simple to find those degeneracies, those irreducible representations, which can appear in molecule. In crystalline solids, translation appears, and you have bands. I would like to finish with the picture of irreducible representations of our favorable point groups, C4V, which I used for iodine. Just a moment, I'll find it. This site gives also the irreducible representations of point groups. And maybe you remember that our point group was C for V. And this is this one. And now I'll try. Who understands this table? And 3 types of labels. This is absolutely incredible. So, our group C4V consists of 8 symmetry operations. We analyze them. 4 rotations around the fourth order axis, and 4 reflections, 2 diagonal planes and 2 Cartesian. 8 operations. What is irreducible representation of point group? This is some group of matrices for which the matrix multiplication law is the same as for group elements. For example, if you have identity element in group, then identity matrix has to be in representation. If you have product of 2 symmetry elements in group, then, and given the third element, then in matrix multiplication also has to be the same. You take matrices from these 2 elements and receive multiplication. After multiplication, the matrix for the third element. So, the representation of group, matrix representation, is a set of matrices which reproduce the multiplication law of the group. As you guess, if you take for all elements of group 1, 1, 1, 1, 1, it always reproduces the group multiplication law. Because when you take 1, 1, 1, 1, for all 8 elements, then you have reproduced this. What is irreducible representation? When you have different sets of matrices, then irreducible is that matrix representation in which matrices cannot be divided in some blocks, in some parts of lower dimension, cannot be reduced. This is irreducible. And from group theory, both for space groups and point groups, there are tables of irreducible representations which are which consist of these irreducible representations. Very simple things are used for their relation. Of course, I will not prove it. It's known from books on group theory. Any group consists of so many irreducible representations. How many elements, classes appear? In this case, it is 5 classes, and first class is identity. Second class is rotation around second of the axis. Third class, these are reflections along Cartesian axis, or maybe Dimon, please show this molecule with C4V. From the presentation, yes, words. Okay. Our group, C4V, consists of identity, element, rotation on 180 degrees around the main axis, 2 times by 9. Reflections in planes 1, 0, 0 and 0, 1, 0. These planes are Cartesian planes. What is 1, 0, 0? This is y 0, z 0, so this is plane 1, 0, 0. And the second plane is 0, 1, 0. These are 2 coordinate planes. Then 2 diagonal planes. You see them. 1 and second. 1, 1, 0 and 1, minus 1, 0. And form rotations around 4th order axis. 4 plus. 4th order axis is along 0, 0, 1. 4 plus by 90 degrees and 4 minus by 270. So our 8 elements are distributed over 5 so-called classes, C1, C2, C3, C4, C5. And the table of irreducible representations of space group gives you irreducible representations of possible matrices. In this case, the dimension of representation is defined for the identity element. So it means that there are 4 one-dimensional representations and 1 two-dimensional. And it's always fulfilled the following very simple relation, that when you have group order 8, the number of irreducible representations equal to number of classes, 5. And you need to divide 8 by 5 squared dimensions, and so you see that it's possible to do only by one way. 1, 1, 1, 1, and 2. 2 squared, it's 4, and 4. If you take, and between them has to be identity. In any group, both space group and point group, always you have identity representation, which has, which is one-dimensional and which is trivial. And the labels of these representations, this is very unpleasant point, used by chemists are this one. They use A and B for one-dimensional. They use 1 and 2 depending on the label around the main order axis. The main order axis is this one. So you see, they have for B -1 and for A +1. Identity representation is always the first. And the class here, you have two-dimensional representation. So if we would have this molecule, iodine fluoride 5, and calculate it, what we would have? We would have only non-degenerate levels or two-degenerate levels, nothing more. How many and which ones? This is our story. For this it's necessary to use site symmetry and special procedure to find the symmetry of molecular orbitals and then understand what happens. The same for phonons. If you are interested in phonons of this molecule, you need to connect each atom. We have 6 atoms, so we have X, Y, Z displacement on each atom position. 3 by 6, 18. 1 is translation of the whole molecule. So we would have 15 different possible displacements. But these 15 are distributed over irreducible representations. But for crystals, situation is more complicated. At this moment I stop. I'm glad that only after your holidays, when you have good time I hope, then you will come and I'll think how to explain you what happens when wave vector appears. Wave vector appears on the screen and it comes from the translation. Okay, so I wish you good...
Maybe questions?
Questions, yes.
See any questions? And,
Next time, next Wednesday,